In today's lesson, we're continuing Chapter 18.2, talking about equilibrium constants. Before we do, let's refresh a little bit about what equilibrium means. If we have a chemical reaction, let's say it's A plus B making product C, a reaction going in this direction, this is called the forward direction, but many reactions are reversible. And when the reaction is going from C back to making A plus B, that would be called the reverse direction. When we have a reaction at equilibrium, it means that the forward reaction and the reverse reaction are happening at the same rate. Okay, so we could have a reaction like this where in our reaction container most of what we have is C. That would be called a product favored equilibrium. If most of what we had in our container was A and B, that would be reactant favored. But both directions of the reaction are happening at the same time at equilibrium and at the same rate. Okay, the equilibrium constant for reaction is the products divided by reactants raised to the power of their coefficients. And it's best to explain what that means with an example. You have nitrogen plus oxygen making 2 nitrogen monoxide. Okay, now this K for the equilibrium constant has no bearing at all to the constant we used for reaction rates earlier in the chapter. This is an entirely different constant. In chemistry we use K a lot for constants, I guess because we can't spell. And so our definition said it was always the products. Now remember, brackets mean concentration. So we're talking about the concentration of the nitrogen monoxide product raised to the power of the coefficient. So this would be to the second power because of this 2 here. And then our denominator would have the concentration of the two products, the two reactants multiplied together. And both of them are raised to the first power because the coefficients in front are 1. Now just reminding you that the brackets mean concentration. Usually it's measured in molarity. Now, when we have data to get a numerical value for the KEQ constant, the equilibrium constant, if the KEQ is greater than 1, it means that products are favored in the equilibrium. If the KEQ is less than 1, it means that reactants are favored in the equilibrium. Let's do another example. Write the equilibrium expression for the following reaction. We've got hydrogen plus carbon disulfide making methane and hydrogen sulfide, and all of these are gases. So our KEQ is equal to the concentration of the methane. It's raised to the first power because its coefficient is 1. Times the concentration of the H2S. It's raised to the second power because there's a coefficient 2 in front. Divided by the reactants. Hydrogen is going to be raised to the fourth power because of its coefficient, and carbon disulfide to the first power. If it helps you to put a 1 there for the superscript, you can. It's not necessary, but you can if that helps you. Now, very important point here in number 5. Only substances that are aqueous or gases go into the equilibrium expression, not liquids or solids. Only things that are aqueous or gases. So, for example, if we have this reaction, this is glucose, C6H12O6. It's a solid reacting with oxygen to make carbon dioxide and water. In this reaction, the water is a liquid. What I like to do so I don't confuse myself is I just like to make a line through the solid and the liquid because they don't go into the equilibrium expression. KEQ is going to be the product, CO2, concentration of CO2 to the 6th power because of the 6 coefficient, and then the reactant, oxygen, also raised to the 6th power because of its coefficient. So the solid and the liquid don't even appear in the equilibrium expression. And then flipping the other side, we're asked to consider the following reaction. Hydrogen bromide gas makes hydrogen gas and bromine gas. And then it tells us at equilibrium it's found that the concentration of HBr is this number, the concentration of hydrogen is this number, and the concentration of bromine is this number. What is the KEQ? And then it asks, are the reactants or the products favored? So let's first start with our KEQ expression. KEQ is always products over reactants. So concentration of the hydrogen times the concentration of the bromine, and they're both to the 1st power because both coefficients are 1, divided by the concentration of HBr. It gets raised to the 2nd power because of the 2 coefficient. Now we're just plugging in the numbers up above. The concentration of the hydrogen is 4.3 times 10 to the minus 1, and the concentration of the, let's see, did I just make a mistake? I did. The concentration of the hydrogen is 2.78 times 10 to the minus 5, and the concentration of the bromine is 2.78 times 10 to the minus 5 as well, divided by the concentration of the hydrogen bromide, which is the 4.3 times 10 to the minus 1. Now I'm leaving off the units because with equilibrium constants, the units don't help us. Now I have to remember that this is squared. Okay, so when I do my math here, I wind up with an answer of 4.18 times 10 to the minus 9th. And there are no units. I'm just writing that just so you know I didn't forget units. We just don't use units for KEQ because they don't help us. Now, the second part of this question was, are the reactants or products favored? Well, this number is very much less than 1, so that means the reactants are favored. Okay, we said if we're less than 1, reactants are favored. If we're greater than 1, then the products are favored. Okay, now another part of this same problem says, what is the concentration of HBr at equilibrium if the concentration of the hydrogen and the concentration of bromine are both 4.87 times 10 to the minus 7 each? Well, I'm going to recopy my KEQ expression down here. Okay, now I have found the value of KEQ in the previous part of this problem, and it's still the same. Now the only thing that ever changes the value of KEQ for a reaction is temperature. Okay, if the temperature changes, the KEQ changes. But you can change anything else. You can change pressures, you can change concentrations of reactants or products, and KEQ numerically stays the same. So now they've told me that the concentration of the hydrogen is 4.87 times 10 to the minus 7, and also the concentration of the bromine is the same thing, so I'm just going to put a squared there since they're both multiplied by the same thing. And then the concentration of HBr, we don't know what that is, so let's call it X. So we're plugging in X, we're letting X equal the concentration of HBr. Now it's squared, let's not forget that. Now we have to do a little bit of algebra. Here, x squared is equal to the concentration 4.87 times 10 to the minus 7 over 4.18 times 10 to the minus 9th. But we don't want x squared, we want x. So if we just square root this, we'll get x, but what we do to one side, we have to do to the other. So x, now hopefully you have a calculator at home that does scientific notation, otherwise the math gets a little bit scary here. Now I don't want to forget that 2 here, I need that. And do my arithmetic, and I get that x is equal to 7.53 times 10 to the minus 3. Now this is a concentration, so it's molar. And remember we said x is equal to the concentration of HBr, so let's just write that here. Okay, so that's what we were asked to find, the concentration of the hydrogen bromide. So in the little assessment that you will have coming up, you'll be given reactions, and you'll be asked to write the KEQ expression. So just remember, it's always products over reactants raised to the power of the coefficients. And then sometimes they'll give you the KEQ, like in this particular problem, and ask you to find the concentration of one of the compounds. Other times they'll give you the concentration of each of the compounds and ask you to find KEQ. But it's really just plug and chug.